So friends, let us have the lecture number 23rd, that is the stability and condition of equilibrium. This is very important topic in the classical mechanics because there uh, the force is responsible for the motion and it is also responsible for the stability and equilibrium of any particular system. So we are going to discuss the conditions by which we can achieve this stability. What are the condition for that and how we can discuss. Later on, I will also try to have one numerical problem because the laws of classical mechanics uh, uh, never be clear if we are not handling the numerical problems for the same. Although online, it's very difficult to discuss almost all the things related to the numerical problems. Even then, I will try to do that. And when you will come offline, then I will discuss that problem on the blackboard because that I think that will give more clarity to you people. So condition of equilibrium means that how the system will be in equilibrium condition. I think I am audible to you people now.
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay. As we have read that only the force is responsible for any disturbance in a body. When it is applied to the body, it accelerates to it. As we have discussed sufficient issues and aspect related to this motion, stability, and the action of the force and the effect of the force on the body under the heading of the Newton's laws of motion. If we want to accelerate, if we want the acceleration to be zero, then the sum of all the forces applied on a particular particle must vanish. Means that if you wish that the particle should be static, then the acceleration should be zero. And acceleration should be zero means that the sum of the forces which are really responsible for the acceleration in the body, that must be zero. So this is the condition of equilibrium of a point particle. If we have a particular point particle means that has been concentrated at a particular point. If we are taking a particular body and that body is concentrated as a particular point, then that is known as the point particle. So for the point particle, it is essentially required that the sum of all the forces which are responsible for the acceleration must vanish because the acceleration has to be zero. Only in that condition, the particle will be in equilibrium condition, or it will be stable, or it will be static at a particular point. It is mathematically expressed as the summation of all the forces acting on a point particle that must be zero. This is equation number 1. The equation can also be written as in terms of the x, y, and z directions at x, y, and z component of each force, and is an expanded form as the summation of the forces acting in x direction should be zero. Summation of all the forces which are acting in y direction, that are also zero. Summation of the forces acting on the point particle along z axis, that must be zero. So these are the form of equation number 1, what has been written in the above bullet point, where Fi means that the force having the suffix I indicate 1, 2, 3 are the forces applied on the point particle. Just if you are talking about the summation over I F I X, इसका मतलब ये हुआ सीधे सीधे कि x डायरेक्शन में F1, F2, F3, F4 सबका जो हम जीरो जब सबका समेशन ले रहे हैं, that is equal to zero. This is the condition for the equilibrium of a point particle. Now we'll have some more aspect for the discussion. In practical world, we deal not only with the point particle. कोई जरूरी नहीं है कि हम पॉइंट पार्टिकल के बारे में ही डिस्कस करें। हो सकता है कोई एक रॉड हो, उसके रॉड के डिफरेंट पॉइंट पर कुछ वेट लटके हुए हों, कुछ मास हो, या वो रॉड इटसेल्फ किसी पर्टिकुलर एक्शन के लिए रेडी हो, किसी पर्टिकुलर वर्क के लिए अप्लाइड हो। तो in that situation, basically, we cannot consider only the point particle. In that situation, the length of a rod is responsible, and the distribution of the forces, as well as the other important aspect related to the force acting on that rod at the different point, at the different position from the point of equilibrium, that must be taken into the consideration. Means that now we are not considering only the point particle, means that the mass is concentrated at a particular point and its stability we wish to discuss. Rather, we have the extended system, that is the rod having the 1 meter length, and some weight are there on the either side or in the middle of that, and some forces has been applied there to rotate that or to twist that or to deform that. In that situation, some special condition must be into the consideration. So that we are going to discuss here. So if we are dealing with that, then the sigma IFI must be 0. The equation can be written as in terms of X, Y, and Z component of each force in an extended form as this. We are considering here point, and on that the different forces has been applied, and we are taking the sum of these forces that must be equal to 0. What will be given here? Or here, if we are extending that in the different directions, and in that direction we have the different forces, obviously the sum of all the forces acting in that should be equal to 0. Similarly, the forces acting on the particle in in y direction, that should be equal to 0. The forces acting in z direction, that the sum of that must be equal to 0. And where fi have the same meaning as usually we have discussed in the last slide, that is the I is equal to 1, 2, 3, means that the force 1, force 2, force 3, force 4, whatever they are acting in x direction and acting in y direction, acting in z direction, the sum of individual directional forces must be equal to 0 for the conditions area. In practical world, we deal not only with point particle, but the extended objects. As example of this is a beam holding a load as shown in the figure 2. Just we are taking this situation. S1, S2, these are two weightage here. And or you can say that these are two stands, or these are the two two places at which this rod has been placed. So obviously some action will be there at the point where S1 we have, and some will be there at S2 there, and load is there, that is one load has been applied on this rod, that is L, and W is the weight of the rod itself. If this situation is there, then what condition of equilibrium will be required? What else we have to consider along with the summation of the forces must be 0? What else should be there? So the beam is in equilibrium under its own weight W and the load L, and the forces on the supports S1 and S2, right, on which the rod has been placed there, that is read here as just as a support. So support S1 and support S2. And if rod has been placed there, then definitely at these supports there will be some force, and these supports will also exert some forces on this particular rod. So if we want to consider the equilibrium condition of this rod, then we have to think about the exerted force at the S1, S2, where the load L, and where the weight of this rod itself. So all these things we have to consider together. To study the equilibrium of such extended body, we need to consider other effects also. That is, beside the acceleration, that we have to also consider. What may be? Anybody of you people, let me know. Beside this force, which is responsible for the acceleration in the body, we have to consider some other thing also, which is responsible for the equilibrium of this particular rod or the body. What may be the other thing?
The mass.
What may be the other?
Center of mass or length of rod.
Anything else? Please think and let me know so that I can proceed.
The mass of the object.
The mass already we have taken. Mass is responsible for the weight of the rod. Weight is equal to mg, and it includes the mass as well as the multiplication with the gravity. That is the weight of that. So that already I have taken here. So, and that is some sort of the force only. There is the W is equal to mg, a kind of force. If we are applying the load, then load will also some kind of force, and S1 and S2 exert some forces are there. Except that something else may be considered for the stability of this particular rod, or only the balancing of the forces is sufficient to describe the condition of stability and equilibrium of this rod. Anything?
So normal forces.
The torque.
Who are you? Who is it? Who is saying torque? Let me know the name.
The Swati.
Really, this torque is also responsible for the stability of this one. So torque should be also taken into the consideration. Why? If you are applying the force, then that force will be responsible for the rotation of this rod, first point. As well as if the rotation is not possible, then these forces may try to deform this rod. It means that the torque acting on the rod should be also taken into the consideration. So one condition earlier to this one, we have discussed that the summation over the force must be equal to 0 for the entire system. And along with, we have to also consider the torque acting on that body with the force, either it is in terms of the load or it is in terms of its weight, either in terms of its normal, which is acting at the different supports there. So in addition to acceleration in the body, a force applied on an extended body can have two other effects. कौन से दो other effects हो सकते हैं? Number one, it tends to rotate the body. अगर हम दोनों तरफ force लगाते हैं, अगर balance नहीं है extended objects पे, तो they can rotate the body. Just we are taking the force at one end and we are taking the force at the other end, then the body will be rotated under the action of that force which is applied at the two sides of a rod. And next, if it is not possible that this may deform the body, these only two effects will be there in addition to the acceleration to the body when the forces are applied to that. And these tendency of the rotation and the deformation can be balanced off to the consideration of the torque acting on that body. And you will see this situation here. If force is applied there and S1 and S2 are two supports there, then under the action of this force, the body will try to rotate by the force will try to rotate the body, or it will try to have its effect just to rotate. And if rotation is not possible, then maybe the bending of that rod will be there. So that is the deformation in the body. Only two action other than the accelerating forces may happen in case of the rod if it is suffering from the force applied on this particular rod. Thus, a beam resting on two supports S1 and S2 tends to rotate clockwise about S2 when a force F is applied downward as shown in this particular figure. That is the figure number 3. The ability of the force F to rotate a body about the point O, for example, if we are taking a particular point that has not been mentioned here, that is the O, is given by the torque, that is the tau generated by it. What the torque has been generated by the force F. Whenever we are talking about the torque, then any fixed point must be required there, about which the rotation is there, or from which position we are calculating this torque, and that torque can be given that the distance of that point from the force, that is the vertical distance, and the force multiplied with that particular vertical distance from that particular point. Now the torque about a point O is defined as the vector product of the displacement vector R0 from the point O and where the force is applied, where the force is, that is R0, rather than R0, if you will say that RO, that is the distance of the force from the point O, then that we can write it here that the torque is equal to R cross F. These two are the vectors here, because in case of the torque, it is also important that either this torque is at the left hand side from the position or the point of action, or it is at the right hand side. According to that, they will bear the sign, either it will be negative or this will be the positive. This convention we have to take in a particular system. If you are solving any problem, then we have to consider either the torque is we are calculating by the force which is the right hand side to the point of action, or it is the left hand side to the point of action. So according to that, we may have the choice of the sign against to that. And this is only just convention. If you are taking only a particular problem, so either you are putting the negative sign for the left side or for right side. It is your choice, system to system. But usually what happened, people used to take the minus sign for the left hand side and the positive sign for the right hand side. So thus the torque is equal to R0 cross F. So here we are taking this particular example, a very simple example that the force which is downward direction that we are taking as a minus F force, and the force which is acting in upward direction that we are taking as a plus F force. So this is known as the moment of the force. Moment of the force, that is the torque, the distance multiplied by the pair of the forces which has been applied on a particular rod or the extended object. For example, if we apply the equal and opposite force at two ends of the rod as shown in the figure 4, the net force is 0, but the rod still has a tendency to rotate. यानी अगर इसको जरा से भी चांस मिलेगा, स्लिप होगा कुछ कोई भी, तो ये रोटेट हो जाएगा. यानी इसकी टेंडेंसी रहेगी. Although these two forces are balancing to each other, maybe that the stability will be there, but the tendency of the rod will be always to rotate in a clockwise direction under the action of the force which has been shown in this figure number 4. So this means that when considering the equilibrium of a body, we not only need to ensure that the net force is 0, but also the net torque about any point O is 0. That is the summation over the torque that must be equal to 0. Means that now we have two conditions for the equilibrium or for the stability. Number one, usually in case of the point masses, if we are taking the summation of the forces equal to 0, then that is sufficient to describe the condition of equilibrium. But if we have the extended objects, then in that situation, not only the force, summation of the force acting on that extended body should be equal to 0, but the torque or the moment of the force, that should be also 0 in that particular system or in that particular extended object. That's why it has been mentioned here, ki summation over I RIO cross FI, that should be equal to 0. In terms of the component, if we wish to write it, then we can say it as a tau 0 x, that is in x direction, O will take its summation over y o f I z minus z I o f I y, and that is equal to 0. So Tanya, you are in meeting.
Yes, sir.
Let me know that from where we are getting this component. How we are writing this tau 0 x is equal to this summation over this one and this one. How we are getting this?
Sir, I don't know.
क्यों भाई, ऐसे कहने से काम थोड़े चलेगा, बोलो. Anyway, Mamta, can you tell me?
Sir, from DLM, what principle?
No. Jyoti, can you tell me?
No, sir.
No. Amrita,
Yes, sir.
can you tell me
Sir.
from where we are getting this one?
सर टॉर्क हम लोग ले रहे हैं एक्स एक्सिस के अलोंग, तो जो उसका मोमेंट होगा, रोटेशन होगा, वो वाई और जेड के अलोंग होगा, वाई और जेड प्लेन में होगा. तो
अच्छा. Deepmala, can you tell me? Deepmala. Rajneesh, can you tell me from where we are getting this component? Suraj,
No, sir.
Vaibhav,
Sir, because torque is constant, so it will be 0 about all directions.
Priyanka Singh, can you tell me from where we are getting this one?
No, sir.
Priyanka Tripathi,
No, sir.
अरे ये तो इतनी कठिन बात तो नहीं है. अरे ऊपर वाला इक्वेशन देखो क्या
सर
है,
ये
वो
क्रॉस प्रोडक्ट है सर.
क्रॉस प्रोडक्ट है ना.
यस
तो
सर,
आप
क्रॉस
जब
प्रोडक्ट.
डिटर्मिनेंट रखोगे आई जे के रखोगे, फिर आर के कंपोनेंट लोगे, एफ के कंपोनेंट लोगे, और इनको जब इसका क्रॉस प्रोडक्ट लोगे तो उनका जो इंडिविजुअल डायरेक्शन में, आई डायरेक्शन में, जे डायरेक्शन में और जेड डायरेक्शन में, वो इंडिविजुअली 0 होंगे. तो एक्स कंपोनेंट 0 होगा, वाई कंपोनेंट 0 होगा, जेड कंपोनेंट 0 होगा. 3 कंपोनेंट इसके आ जाएंगे, जैसा हम लोगों ने फोर्स के केस में देखा था. तो दैट इज द सेम थिंग. You people have read this all the vector calculus and vector algebra, even then you are saying that I don't know, I cannot tell. It's very simple कि ऊपर लिखा हुआ है कि ये क्रॉस प्रोडक्ट है RIO और FI का. तो इनके सभी कंपोनेंट का आप क्रॉस प्रोडक्ट लो और उनके जो इंडिविजुअल कंपोनेंट हैं उनको 0 कर दो. Then we are getting this expression. Simply we are getting this for y direction, this we are getting for the z direction. I think that there is no problem. And if Fi, where this Fi have the usual meaning as you people have read it as I is equal to 1, 2, 3, what type of how much number of the forces are there along x axis, along y axis, and along z axis, that we are considering here, as well as the vector for the r that has been indicated, that xio, YIO and ZIO. So anybody have still any problem to understand this one, how we are writing that the tau 0x, tau 0y, tau ox, tau oy, and tau oz? Anybody have any problem to understand this one?
no, sir.
So
No, sir.
okay, so let us continue. Here, in view of the above discussion, the condition for the equilibrium
me, sir.
of rigid bodies can be summed up as number one.
Excuse me, sir.
Yes.
Sir, the previous point which was mentioned, that even if the net force is zero, still
Uh-huh.
it has a tendency to rotate. And
Okay.
this
Okay.
point, this is mentioned that this means that when considering equilibrium of bodies, we not only need to ensure the net force is zero, but also the net torque about any point
Okay.
goes zero.
That's way. That is
Sir, then
that.
if sir, if the net force acting on a body is
Okay.
zero, it means
Uh-huh.
the force are balanced. Then how
Okay.
is torque working on the body? Like I can't imagine that
Acha,
situation.
just, just you are saying, for example, I am telling you people, कि just you are raising your hand in the horizontal direction. Okay. In
Okay,
horizontal
sir.
direction, you are raising your hand. Just you are taking the pledge for anything. Na? You used to stretch your hand. Na? Then
Yes,
what
sir.
happened? At the other end of your hand, there is the gravity towards the earth side. And
Mm.
in order to have a straight position of your hand, your muscular force or your muscular energy given by your body at the joint of your body to the hand, that is supporting that it should be straight there. Although
Yes,
the forces are balanced by your muscular force as well as the gravity towards the earth, but are you relaxed there?
no, we can feel
Why?
the effect that.
Why you are feeling that? Although the force is net force is zero there. So in that tendency, there is a tendency in your hand that we are feeling some pain. Just I'm giving this live example so that you can realize. Although I can take this example for the lead for the dead bodies also. For dead bodies means that the dead objects also. But here, if you are realizing that, na, then it will stress in your mind that although our hand is static and it is in condition of equilibrium under the action of the force supported by my body, and it has been stressed or it has been attracted towards the earth, even then we are feeling some uneasiness to that, unrest to that. And that unrest is again realized by the body under the action of the minus F and F force, although these two has balance to each other. Clear or not?
Okay, sir. Okay.
दैट इज द टेंडेंसी, जस्ट टू टेंडेंसी टू दैट कि भाई अगर आपने दोनों फोर्स लगाए हुए हैं तो वो फोर्स बैलेंस तो है, लेकिन वो बैलेंस जरूर है लेकिन उस ऑब्जेक्ट पर लगे तो हैं। अगर वो एक ही दिशा होती उनकी, यानी जो
Yes,
टिप
sir.
ऑफ फोर्स है
Yes, sir.
ऊपर और नीचे बराबर होती तो एक दूसरे को 100% वो कैंसिल कर देते। हो सकता है उतना अनरेस्ट, जैसे मान लीजिए आपने ऐसे कोई बॉडी लिया और जस्ट नीचे की तरफ जितना है उसी को ऊपर धागे से आपने बांध रखा है, ठीक है ना? तो तब तो मान लीजिए दोनों के टिप ऑफ फोर्सेस एक दूसरे को बैलेंस कर रहे हैं, लेकिन अगर टिप ऑफ द फोर्सेस आर एट द डिफरेंट प्लेसेस, then the situation will be unrest situation. There will be the tendency for the rotation of the body, and that is the cause for the torque and that body that is unseen to that. Okay,
Yes, sir.
I
Thank you.
should I think I should proceed now.
Yes, sir. Yes.
So, in view of the above discussion, the condition of equilibrium of rigid bodies can be summed up as number one, zero acceleration should be there. The body as a whole should not accelerate or move. Number one point. This is ensured if we are having the condition that the summation over Fi, that is the sum of all the forces acting on the body, is zero, irrespective of where on the body these forces are applied. Number one point. This is the point of remark here. Okay, whatever the position for the action of that, but the summation should be equal to zero. That is what you are saying. Okay, the forces are acting at the different end of the rod, and although they has been balanced, and they has been cancelled to each other. Even then, why we can realize that the tendency of the rotation of the body is there. So here, just I'm taking the condition. Whatever the position for the action of the force on the body is there, that summation should be equal to 0. Just it happened in case of minus F and F forces there. That is the summation over I should be equal to 0. Or equivalently, we can say that in a respective direction, the summation should be equal to 0. That is in X direction, that is in Y direction, that is in Z direction individually. For example, if we are taking the figure number 2, if F1 and F2 are the forces acting and the support in the vertical direction, then we may have F1 plus F2 plus W plus L, that all should be equal to 0. Just with the figure has been shown to you in the start of very beginning in the figure number 2. The rod was supported by the S1 and S2, and the W was the weight of that rod, and L was the load applied to that rod. And if we will have the numerical value of the same, then F1 plus F2 plus W plus L, that is equal to 0. And next condition for the same is that the zero net torque, that is R the moment, the sum of the moment of the forces about any point in the body should be 0. That is, we will write here summation over I tau IO, that should be equal to 0, exactly in the same manner as we have realized it in case of the force acting on that body. So where tau IO is the torque due to the force Fi about the point O, the two conditions mentioned above are necessary for the equilibrium. That is, to achieve the equilibrium, they must be satisfied. And it turns out that for rigid bodies, these conditions are also sufficient to guarantee their equilibrium. Means that these two things we have to think into the consideration whenever we are talking about the condition of equilibrium of a body. Let us take a particular example. This very lovely example I have taken here. The 1000 Newton weight. 1000 Newton weight means it is the combination of the mass and gravity. तो ग्रेविटी अगर हम 10 ले लिए तो 100 किलोग्राम का एक मास हो क्या रहा है इसका कि is to be lifted using the light weight but strong rod as a lever shown in the figure. अभी फिगर में दिखाई देगा, एक हमारे पास रॉड है जो लीवर का काम कर रही है, और उसी लीवर से आपने कई बार देखा होगा, दिस इज वेरी ओल्ड एंड एंशिएंट वे टू लिफ्ट the heavy weight or heavy bodies there. And I think that this technique has been used by the people long back, 1000 years back. कि उनको हो सकता है इसकी मैकेनिक्स तो नहीं पता रही होगी, लेकिन हेवी बॉडी को उठाने के लिए लीवर और फल्क्रम, इन सभी चीजों का बखूबी प्रयोग किया जाता था. तो यूजिंग द एज ऑफ अ ब्रिक, जैसे आप कभी देखे होंगे, अब पता नहीं शहर में इतनी अवसर मिलता है कि नहीं मिलता है, गांव में जो बच्चे रहते होंगे वो देखे होंगे कि मान लीजिए कोई बहुत बड़ा सा लकड़ी का कोई टुकड़ा है, उसको उठाना है तो पहले एक ईंट लगाई जाती है, ईंट के ऊपर एक रॉड या एक कोई लकड़ी जो मजबूत रहती है वो लगाई जाती है, और उसके नीचे डाल करके ऊपर की तरफ जब फोर्स लगाया जाता है तो लकड़ी उठ जाती है. ये टेक्निक just the layman use it frequently, but they don't know ki, what the mechanics is there, what is the physics is behind to that. So that we have to discuss, that we have to study just to the real problem. I have taken this real problem कि क्या हुआ भाई कि ये रॉड जो है एक लीवर की तरह इस्तेमाल हो रही है, और हम एक ब्रिक लिए हुए हैं जो फल्क्रम के रूप में इस्तेमाल कर रहे हैं, और उसकी हाइट दी गई है कि वो 6 सेंटीमीटर के हाइट का एक ब्रिक है. एंड व्हाट द फोर्स शुड बी अप्लाइड ऑन द अदर एंड ऑफ द रॉड टू लिफ्ट द वेट. अगर हम उस भारी कोई बॉडी है, लकड़ी है या कोई चीज है, उसको हम उठाना चाहते हैं, तो हमें उस रॉड के दूसरे एंड पर कितना फोर्स लगाना पड़ेगा। टेक इनटू अकाउंट द फ्रिक्शन बिटवीन द ब्रिक एंड रॉड। ये बहुत बड़ी बात है कि आप इस प्रॉब्लम को इस आईने से भी डिस्कस करिए कि अगर वो ब्रिक और लेबर के बीच में फ्रिक्शन लगता है या नहीं लगता है, then what will be the situation for the same? So that we have to take. Sometimes you might have seen that the thing slips there, और ऐसा स्लिप होने की वजह से आप उस हेवी वेट को नहीं उठा पाते हैं। अगर आप लोगों ने इसको उठाते हुए कभी देखा हो तो फेलियर और सक्सेस ट्रायल ये सब चलता है जब हम लोग ऐसा काम करने जाते हैं तो, एंड बाय दैट ट्रायल वी यूज टू से दैट something is wrong with that, and some efforts should be made so that the slipping should be avoided there. अब वो क्यों हो रही, कैसे हो रही, साइंटिफिकली तो ये नहीं जानते हैं, लेकिन उसको वो करने की कोशिश करते हैं। जस्ट आई हैव ड्रॉन दिस फिगर लास्ट नाइट कि हमने ये एक रॉड लिया जो लंबी सी रॉड है, एक पर्टिकुलर इंक्लिनेशन पे है, थीटा इंक्लिनेशन पर है, और दूसरी तरफ एक 100 किलोग्राम का मास रखा हुआ है, उसको उठाना चाहते हैं, और इसके नीचे एक ईंट रखी हुई है, वो ईंट की ऊंचाई 6 सेंटीमीटर है। थीटा एंगल इस एज के साथ रॉड बना रही है, और सीधे सीधे जो वेट उठाना है उसके नीचे इसको घुसाया गया है, इसको घुसा करके उसे उठाने की कोशिश की जा रही है। जो फोर्स लग रहा है दूसरे रॉड के एंड पर वो नीचे की तरफ लग रहा है, और हमने अपनी कन्वीनियंस के लिए ये मान लिया है कि जो रॉड की लंबाई है वो 100 सेंटीमीटर है, या 1 मीटर की रॉड हमने ले लिया है। तो एक स्केल ले लिया कि 1 मीटर की रॉड है, और जो इसकी दूरी है जहां पर ये फल्क्रम के रूप में से इस्तेमाल किया जा रहा है, उसको हमने मान लिया कि मान लीजिए 10 सेंटीमीटर है। ये आपके ऊपर था कि आप कोई भी सेंटीमीटर ले सकते हैं इसके ऊपर, और ये 6 सेंटीमीटर इसकी ऊंचाई दी गई है। इसकी ऊंचाई को और कुछ भी माना जा सकता था, लेकिन बहुत ज्यादा ऊंचाई माने जाने पर इसको सॉल्व करने में दिक्कत होती। सॉल्व करने में क्या, ये जो रियल प्रॉब्लम है वही शुद्ध दिक्कत में आती। तो इसके लिए इसकी हाइट और इसकी पोजीशन, इन सब इस बात पर निर्भर करते हैं कि व्हाट value of the force is required to lift this weight of 1000 न्यूटन। तो इस फिगर को आपने ध्यान से देखा तो उसमें 2-3 पॉइंट्स आपको बहुत अच्छे से दिखेंगे। नंबर 1, जहां रॉड उस ब्रिक को सपोर्ट कर रही है वहां पे फोर्स लगेगा, और उस पर जो नॉर्मल फोर्स है ऊपर की तरफ एन की डायरेक्शन में है, और ये जो वेट है यहाँ पर है, वेट तो हमेशा नीचे की तरफ 100% होता है, दैट इज इन द टूवर्ड्स द डाउनवर्ड डायरेक्शन। और यहाँ जो फोर्स लग रहा है, हम जो फोर्स लगा रहे हैं रॉड पर, हम नीचे की तरफ लगाएंगे जरूर, लेकिन ये 100% नीचे की तरफ लगेगा नहीं, क्योंकि हम रॉड पर जब लगाएंगे तो इसके इंक्लिनेशन के हिसाब से इसके जो कंपोनेंट होंगे वो ही नीचे की तरफ होंगे, दूसरे कंपोनेंट किसी और चीज को बैलेंस करेंगे। तो आइए हम देखते हैं कि कैसे इसको डिस्कस करने की कोशिश करी है। ऑल्दो दिस प्रॉब्लम कैन बी डिस्कस इन बेटर वे ऑन द ब्लैक बोर्ड, कि सारी चीजें सामने हों और सारी चीजें आपको विजुअलाइज करके दिखा दें। समटाइम्स ये भी हो सकता है कि इसमें कुछ जैसे एन के ही कंपोनेंट हैं, तो एन के कंपोनेंट, अगर हमें एन का कंपोनेंट निकालना है तो एन का कंपोनेंट निकालने के लिए हम पहला काम क्या करेंगे, बताओ भाई। एन का कंपोनेंट हमें निकालना।
So we'll break it into n cos theta and n sin theta.
तो वो cos थीटा कहाँ होगा?
सर
थीटा
वो
कहाँ?
सर बेस से जो एंगल रॉड बना रहा है वो थीटा बना रहा है, तो सर बाई ज्योमेट्री अगर हम ऊपर जाएंगे तो एन जो है सर, एन और जो ब्रिक आप रखे हैं उसके बीच का एंगल भी थीटा ही होगा।
हाँ, इसका एक थ्योरम है कि अगर इंक्लिनेशन के बीच में एंगल है तो उनके नॉर्मल के बीच में भी वही एंगल होता है, कह जाएगा ना। तो जो ये ब्रिक की एज को आगे हम बढ़ा दें तो एन से जो एंगल बनेगा वो थीटा एंगल बन जाएगा। गुड। तो उसके डायरेक्शन में जो हम एन का कंपोनेंट लेंगे तो एन कॉस थीटा हो जाएगा। और जो रॉड की डायरेक्शन में कंपोनेंट लेंगे वो सीधे सीधे एन साइन थीटा हो जाएगा। और यही एन साइन थीटा आपको जो है या एन कॉस थीटा जैसे भी होंगे आप लेंगे, ये तो कन्वेंशन पर निर्भर करता है कि किधर इसको ब्रेक करते हैं। यही इसके फ्रैक्शन को, इसकी फ्रिक्शन को जो एफ है उसको बैलेंस करेगा। तो अगर हम इसके कंपोनेंट लेंगे तो इन कंपोनेंट की बैलेंसिंग कैसे होगी, यू कैन सी हियर इन दिस प्रॉब्लम। इफ देयर इज नो फ्रिक्शन बाय ब्रिक, पहले तो हम कंडीशन करें कि भाई फ्रिक्शन ही नहीं है ब्रिक और उस रॉड के बीच में। द फोर्स एफ अप्लाइड बाय द पर्सन कैन नॉट बी ओनली इन वर्टिकल डायरेक्शन एज दैट would not be sufficient to cancel the horizontal component of n। उसका जब तक हॉरिजेंटल कंपोनेंट बैलेंस नहीं होगा तब तक उस पे फोर्स लग नहीं पाएगा, वो स्लिप करता जाएगा। एंड let us consider there is no friction, then the rod will slip, and if there is friction then the rod will not slip, obviously. Let us apply the equilibrium condition in such situation. The balance of the forces gives that the summation over f is equal to 0, that is the n sine theta minus f cos theta in x direction। यानी x direction में जो नॉर्मल का कंपोनेंट है और एक्स डायरेक्शन में फ्रिक्शन का कंपोनेंट है, दोनों को देखेंगे, दोनों अपोजिट डायरेक्शन में होंगे और उनका जो डिफरेंस होगा वही एक्स डायरेक्शन में लगा हुआ फोर्स होगा। सिमिलरली वी विल टॉक अबाउट द एन कॉस थीटा प्लस एफ साइन थीटा, जो नीचे की तरफ, और ये एन कॉस थीटा ऊपर की तरफ लग रहा था, और ये 100 न्यूटन का जो फोर्स है वो वेट ऑफ द बॉडी है वो नीचे की तरफ है, इसलिए माइनस साइन है, और एफ हम नीचे की तरफ लगा रहे हैं, दैट इज माइनस एफ इन जे डायरेक्शन, दैट इज इन वाई डायरेक्शन, दैट ऑल विल बी इक्वल टू 0। तो अकॉर्डिंग टू द लॉ, अकॉर्डिंग टू द प्रिंसिपल, we have already discussed the summation over x direction, y direction, and individually that will be equal to 0. That will be equally, individually will be 0. Similarly, we will talk about this y component. Then we will write that n cos theta plus f sin theta minus 100 minus f is equal to 0. And these conditions give that n sin theta is equal to f cos theta, and n cos theta plus f sin theta minus 100 minus f is equal to 0. Let us choose, just we have equated the x and y component individually as a 0. So let us choose the fulcrum as the point about which we balance the torque, क्योंकि extended object पे जो condition of equilibrium लेंगे, that will be also we have to take the torque into the consideration, and then the summation over that torque, that should be equal to 0, and that the summation has been taken here 0.9 r, means that 90 centimeter we have taken, and I have multiplied it by the f force. And similarly we will talk about इसमें एक चीज छूट गया है, माइनस होगा इसमें, माइनस 0.9 होगा और दूसरे वाले में दोनों माइनस होंगे, एंड व्हेन वी विल इक्वेट इट एज अ 0, देखो दूसरे पक्ष में मैंने ले भी लिया है कि माइनस क्यों ले रहे हैं और f को हम क्यों प्लस ले रहे हैं, इन दोनों के बीच में ये हम जो दोनों पार्ट लिए हुए हैं टॉर्क के संबंध में, एक में डिस्टेंस को हमने जो है लेफ्ट साइड में कंसीडर किया है, दूसरे में जो पॉइंट है फलक्रम का पोजीशन है उससे राइट साइड में, एक को लेफ्ट साइड में, इसलिए हम इसको एक में नेगेटिव एक में पॉजिटिव लिया। और बेसिकली इसमें f को नेगेटिव लेना था, तो f नेगेटिव है, 90 सेंटीमीटर आपका राइट हैंड साइड में पड़ रहा है, तो ये हो जाएगा -0.9 cos थीटा f, और दूसरे वाले में अगर हम लेंगे ये, तो ये चूंकि हमारा जो फलक्रम से लेफ्ट हैंड साइड में है इसलिए 10 सेंटीमीटर वो भी माइनस है, और 1000 न्यूटन नीचे की तरफ लग रहा है वो भी माइनस है, लेकिन ये x और y डायरेक्शन में इनके कंपोनेंट लिए गए हैं, एंड दैट gives the idea that gives the idea that is the minus 0.9 cos theta f plus 100 cos theta, and that will be equal to 0. Finally, f will be calculated that f is equal to 111.11 Newton, and the normal force and the frictional force can now be calculated with the other two equation obtained above by the force balance equation, and we'll have n is equal to 111.11 cos theta and f is equal to 1111.11 cos theta, and where from the figure cos theta is equal to 0.8 and sin theta is equal to 0.6, जो वहां ट्रायंगल बन रहा है ब्रिक की वजह से, उसके सहायता से cos theta और sin theta की वैल्यू निकाली गई है. And finally we'll have the n is equal to 888.9 Newton and f is equal to 666.7 Newton. So actually this problem, once you should go through this problem, and if you have any problem, then I will discuss later also. And when you will come offline, then I will solve this particular problem of the mechanics on the blackboard, so that much clarity should be given to you people. So I think this is all about of today, what I was interested to discuss with you people. Any problem or anything what you asked to related to this discussion or related to this lecture?